Hey,
Okay, we are
good
live.
evening.
All right, let me refresh this page and welcome everyone to the next live stream for week 5, which is session 4. And numbering system's a little weird. All right, so first thing, if you're watching on an LMS, open it up in YouTube so you can use the chat. Or if you have a look in the chat in YouTube and you want to join the Hangout, you can. Just click on the link. There's a little bit of a delay. All right. So first things first, let's have a look at some of the questions from the quiz that people had problems with. That's not what I wanted to do. All right. So the first question I had up here, and it's disappeared. It's this one. All right. So the first question I had here is this one. Most people struggled with this one. I don't have the exact number of people. All right. So this one involves arrays, a little bit of ASCII, a for loop, a while loop, incrementing. It's got quite a bit of things happening. So let's have a look line by line what's happening. All right. That's not what I wanted to do. Yep, that's it. All right. So in the first line, we have, that's not dark enough. We have int num 4, and we initialize each of the elements to 0 using this. So to draw that out, we have num, and it is an array of 4 ints. And this is element 0, this is element 1, this is element 2, this is element 3, and they all have 0 in them. And they're all ints. Int, 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 int. Okay, so we've looked at that line. Oops. Now let's look at the next line. So in the next line, we have another variable being declared. And this is int count equals 0. So we've got a variable called count. It's an int, and it's a value 0. Next line, we have a while loop. So we've got while count is less than 6. Then we have car, I'll write all this out, ch equals get car. And then have an if, two and, a logical and, D. Then have some braces. Then we have num. We're selecting the element, which is car minus A, plus plus, semicolon, and then plus plus count. All right, So we won't look at the for loop yet. Hey Josh, can you do me a favor before we go any further?
Sure.
Can you check up the
Yes.
Cool.
On LMS?
Right. Yep.
Sure.
All right. So we're here.
Just doing that now.
So we check, is count less than 6? Yes, it is. So that's all good. So now we go to this next line and we create a new variable called ch, and it's a character. So let's draw another variable here. It's of type car, and we don't know what's in it yet. At the top here, we've got an input. So our input is A, B, I might do that in a lighter color. A, B, C, D, A, B. So when we do getCar, we grab the first character off the buffer, which is A, and store it in here. Then we go to the next line and check, is CH greater or equal to A and CH is less than or equal to D? It is A, so we know that it is equal to A. Now, this is doing a numerical comparison, so it's actually looking at the value, the ASCII value of A. If we get up the ASCII table, now you don't actually need to know the value for this question, but if we wanted, the value would be 65 decimal. So this number's 65, and B would be 66, C would be 67, D would be 68. All right, so now we go to the next line, and we're doing what's in here. So we've got A minus A. Now, we know A is 65, so our result would be 0. So num 0 plus plus, meaning that the index 0 would get incremented. So, oops, we now have a 1 in here. All right. Next, we go to the next line, and we increment count. So count now is going to be a 1. Then we get here, and this is still in a while loop. So we'll do the next one in green. Oops, didn't mean to do that.
Broke it.
It's not going to zoom where I was before. So we go back up to here, and we check. Is count less than 6? Yes, it is, because it's 1. We then get here. Now, car is also already defined, but that's okay. So now we get rid of what's in here, and we store the next thing on the buffer, which is a B. which is value 66. Then we check here, is character between A and D? Yes, it is. So we go down here. B minus A is 66 minus 65. So we get a 1. And we have a 1 here now. So the one at the first index, well, the second index, index 1, will now become a 1. Cool. So we've done that, and then we increment count. Now count is 2. Now we continue. Count is still less than 2. Then grab the C, which is 67. C minus A, or 67 minus 65, is 2. Now you don't need to know these numbers to work this out. C minus A is 2. Num 2 plus plus, so we get a 1 here. Then we go back up again. We increment count again. So we get a 3. We go back up again. 3 is less than 6. We then grab the lowercase d. Now, be careful, the lowercase is not the same as an uppercase. So if we look at our ASCII table, the lowercase, what is it? Lowercase d is 100, where uppercase d is 68. They're different letters. So we now have the letter D in here, which is value 100. This is not between the range of uppercase A and lowercase d. So it will skip this part. Raul, cool. Okay, so this becomes 4. Go around again. We grab the next character, which is an uppercase A. So that's 65 again. 65 minus 65 is 0. So we increment this one. Now this has got a 2 in it. And increment count again. Now it's 5. We go back up. We grab the B. So this now has a B in it. This is getting messy. This has 66. B minus A is going to 66 minus 65. I'll just get rid of that. And now we have a 1 here. So this becomes a 2. Then we get here and we increment count. So count is now 6. We go back up. Count is not less than 6 anymore. So now we have to go down. So let's get all this and resize it. Oops, not rotate. So I've done all that. Oops. So now let's look at the next part, which is this part. So we've still got 2 here. We've got 2 here. We've got 1 here. Now, car is only local between these 2 braces. So actually, once we've left that loop, car is actually gone. The wrong thing. So this doesn't exist anymore. Our count still exists because it's outside of that loop when it was defined, but this isn't. this is gone. And that was just working out. So currently, we've got 6 here. Now we're going to the for loop. So for, Josh made a mistake. It depends which version of C you're using. But
Did I make a mistake?
int I.
Oh no, I did too. Damn. Sorry.
You might want to take a note of that.
Yeah, I might. Because I can't edit the question. That's really annoying.
You can.
I can.
Yeah, in the
Okay,
question.
I'm gonna do that now. Cool. I'll do that now.
Okay, so now we're here. First, this should be up here, but that's okay. We declare I. So we've got a new variable I, which is an int. We then initialize I to 0. Is I less than 4? Yes. So now we go here. So we've got num 0 times equals 2. Now that's the same as saying num 0 equals num 0 times 2. So let's have a look at num 0. It's 2. 2 times 2 is 4. So our new number inside num 0 is going to be 4. Oops. Cool. All right, so now we go back up. First thing we do is increment I. So I is now 1. One is less than 4, so we go back in here. Num 1 times 2 is going to be 2 times 2, which is also 4. So now we've got a 4 in here. Then we go back up again. I is now 2. 2 is less than 4, so we can continue. This is going to be 2 now. 2, 2. We have a 1 in here. 1 times 2 is 2. So now we have a 2 in here. We go back up. I is now equal to 3. 3 is less than 4. So now we can do num 3 times 2. 0 times 2 is 0, so this stays the same. Then I goes to 4, goes back up, increments, and goes to 4. 4 is not less than 4. So we exit, and we do the last bit. All right, the last bit is the printf. So we have printf cent d, cent d, cent d, cent d, num 0, num 1, num 2, and num 3. It's bad squeezing in, but I think you get the point. So when this prints, this first format specifier will look at the first argument after the string argument, and it will grab num0, which is 4. So on our screen, we'll get a 4. The next one, we get a 4. The next one, we get a 2. And the last one, we get a 0. And so the answer would be this one. Does that make sense? Any questions about this question? All right. Cool. All right. So I'll get Josh to go through the next question. If you want.
Cool.
Can I go through the next one?
Yeah, I'll do the next one. Yep. Which one is the next one?
The next one is W5B1.
W5B1. Awesome. Are you using your screen? You can do the writing? Or do you want me to share screens?
I'll give it to you.
Okay.
Two.
Hey?
Yep.
Just loading up the things. Won't be a second. Share screens. Go that one. Share. Cool. Can you see my screen?
Yep.
Awesome. All right. So the question we've got here, this question here, or these types of questions, are similar to the CryptoLock question that we had in Lab 3. So we should be familiar with what we're doing in this problem. So Lisa has an 8-bit lock, which she stores in a variable named lock. So what we've got is lock. And this is where she's going to be storing the crypto lock in. It's 8 bits as well. So let's just write that down. 8 bits. Cool. So to lock the lock, Lisa wants to set. So set is probably a keyword, especially because it's underlined. So we're setting bit 0, bit 3, and bit 7. All right, so let's just look at how that looks. So we've got 8 bits. Now we want to set bit 0. So all right, so we want to set bit 0, which is this one here. We want to set bit 3, so 0, 1, 2, 3, this one here. And we want to set bit 7, which is this one here. So remember, with our bits, they start at bit 0. So bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7. Awesome. So which of the following lines of code are we going to use to achieve this? So inside our lab that we had, we only set a single bit at a time. But this time around, we want to set 3 bits at a time. So this problem's a little bit different to what we've seen. The first thing we need to remember is how to set a bit. So remember, when we're setting bits, that's the OR operation. Now, if you do forget these or what they mean, you do have the Lab 3 document, which lists which operations, so which operators are used to set, to clear, to test, or to toggle bits. So the first thing we need to realize is we've only got 3 possible outcomes from this. So now we need to work out, what do we use to set it? And if you were in the live stream last week, I went through how you can actually convert whatever this is into a hex representation. So on your computer, you'll have just the calculator program. So what you can do is you can jump into the menu here, click on Programmer, and depending if you've got Windows 10 or Windows 7 or 8, yours might look a tiny bit different. But what we want to do is we want to grab up the binary input, and we're just going to type this in as it is. So 1, 0, 0, 0, 1, 0, 0, 1. And now we're going to convert that to hex. So you'll see up here, this is the same as 89 in hexadecimal. You can also see what it is in decimal and octal, but we're only interested in the hexadecimal because we know that when we see a 0x, we're talking about hexadecimal. So that's pretty much our answer. We can see that we need to set the bit, so we need to use this OR operation. And what we OR it with is 89 in hexadecimal. So we can see that B will be our answer here. So really important to make sure you do use this calculator tool. You've got it when you're in the labs, you can use this. Also on your computers if you've got a Windows computer. Because these sorts of questions, they're pretty straightforward. Once we've done the lab, we know how to use these things. We know what the OR is for, the AND is for. Yeah. Did you want to add anything to that, Matt?
Not really.
Really?
No, I don't think so. I think most people are able to convert now. I think.
Yeah. Does anyone that's listening have any questions on that? Nope. Awesome. Cool. What was our next question?
All right. Do you want to go through week 5, FH5?
FH5. Alrighty. So let me just do that. Fantastic. So, alright, we've got a program. What is the output of the following C program? So we're including the standard in our library. We've got an integer variable. We're initializing it to a value of 0. Notice how this is outside of our main function. So we'll look at this soon. We'll go through the program. We'll come back to this here. We've also got a function. So this is a function prototype up the top here. Remember that we need our function prototypes before we have our main, and then we have the actual function definition after main. So we've got a function here. It's called func. It takes in one integer parameter, and it returns an integer. Cool. So going through our program, we've got an integer x equals func of 4. So what we need to do now is we need to look at our function, and we need to note that this 4 here is going to be passed in as this parameter. So for our function down here, whenever we talk about x, we're actually talking about the number 4. So just remember about those parameters and how they work. So now let's have a look. I'll get the black pen over here. So we might have... So this is for our main, and this is for our... Okay. So, all right, in our function, straight away what we saw is for the first time, we've got x equals 4, because we saw that this 4 is being passed into this x variable here. And then we've got a temp variable, and we're saying temp equals external plus x. Now this is when we need to look into what external is. So we know that it's a variable. We know that we haven't seen external inside this function before. And we know that all the variables that are inside our main function, we can't actually see from inside our func function. So we saw before that this external variable was defined or declared at the very top of our program. And we call this a global variable. So what this means by a global variable is anything in our whole program, so including our main function, including our other function here, they can both access this external variable. So whereas inside our main function, for example, this integer x, we call this a local variable because we can only talk about this variable when we're inside our main. So what we might do at the bottom here as well is, well, we've got this external variable. And we saw it equals 0. So when we get down here, we've got temp equals. We need to look at external. We see external has a value of 0. So temp equals 0 plus 4, because remember this x that we're talking about is this x here. So temp just simply equals 4. And then what we're saying next is external. So again, external here, we're talking about this global variable. We're saying that it equals x. And just remember, x here, we're talking about the local variable x, which comes in through this parameter here. So over here, we saw that x was equal to 4. So what we're going to do is we're going to overwrite the value stored in external and replace it with 4. And remember that external is a global variable, so anything can access that variable. So if we talk about external again from anywhere in our program, it's going to have a value of 4. Now we're going to return temp, so we know that when we return a variable, we grab whatever the variable temp is at the moment, so temp is equal to 4. We replace that into here, so we're effectively saying int x equals 4. So if we go over here, in our main function, x equals 4. So this was, just for this first line of code, it was pretty involved, but it's really important to understand the process that we went to do this problem. So next up, in our main, we've got a variable y. So we're saying y equals func of 2. So again, we're going to be grabbing this 2, replacing it for the x. So I'm just going to get rid of these for now. So now x is equal to 2. Then we're saying temp is equal to external. Now again, external is this global variable. So we look at what's stored in external, which is a 4. So temp is 4 plus x, which is 2. So that will equal 6. Now we're saying external equals x. So we're looking at the value stored in x. It's a 2. Remember, we're talking about the local x. So the x from our function called func. So we grab that 2. And we replace external with a 2. So now we've got external as 2, we're returning temp, which means we grab this 6, we replace it where we said func 2. So now we're effectively saying y equals 6. And now finally we're going to do it with z as well. So we've got z, we're saying func of 3, so we grab that 3, put it in for the x, like so. Then we're saying going to be saying temp is equal to external. External is 2 at the moment. So temp is 2 plus x, which is 3. So that just equals 5. Then we're saying external equals x. So we're grabbing this x here. And then we're overriding what's stored in external, replacing it with a 3. And then we're returning temp. So we're grabbing this temp variable, and we're replacing it with the function call, func3. So now what we find is after that, z just equals 5. Cool. And then finally, we've just got a printf statement. So we're printing out 3 integers here. The first one is x, the second one is y, the third one is z. So our output should simply be 4 space 6 space 5. So we should find that E is our answer here. Now it is something to be very careful. We had a few different things going on here. We had an x variable here that was local to our main function, and an x variable here which was local to our func function. So be really careful about what variables that you're talking about when you do these functions. And also do be careful about this variable external, which is a global variable, because it's easy to get tricked by that too. Now, does anyone have any questions on what we've just been through in YouTube or the Hangout? Or did you want to add anything to that, Matt?
No, I don't.
Cool.
Right. W5A1.
W5A1. Oops, that's AH1. A1, cool. All right. So what we've got here is the following array declaration. declaration and initialization legal? If so, what is the value of myArray 4? Cool. So what we've got here, just by looking at it, we've got int myArray 7 equals 1287. All right, so the first thing we need to realize here, we'll forget about the initialization. We'll just look at the declaration for the moment. So this says that we're declaring an integer array. We know it's an array because we've got these square brackets, and we've got the number 7 in there. So what that means is one, two, three, four. I did that terribly. 1, 2, 3, 4, 5, 6, 7. Cool. So what it means when we're making an array that can hold 7 elements. So we have 7 of these cells. So this is cell 1, 2, 3, 4, 5, 6, 7. And we know when we're talking about our arrays, we have the index of the array starts at 0. So I'm just going to include these on the top here. All right, so to answer the first question here, we know that the declaration of the array, so int myArray 7, that looks good. Let's look at the initialization and what we're doing here. So we have our curly brackets. So this is actually allowed. This is actually how we can initialize our array with some numbers. So one thing to note which might get a bit confusing is we've only got 4 numbers here, but our array is of size 7. So let's start inserting these numbers and let's just see what happens. So what we're saying is the first element in our array should start with the value 1. The second element in our array should start with the value 2. The third element in the array should have the value 8. The fourth value in the array should have the value 7. Now, we've still got these 3 extra cells left. So what actually happens is because we haven't said what we want to start them as, we just say that they're 0. So we've explicitly stated we want these first 4 elements to have these values. We didn't say anything about these elements, so C just says, well, I'm going to make them 0. What we've seen so far is the declaration and initialization is completely legal. We're definitely allowed to do this. So we've got B and C. Those are not correct. So we've only got A, D, and E. We also see the syntax is correct. This is completely legal to declare an array and initialize it. So we've only got A and E left. So having a look, what is the value of myArray 4? Remember when we talk about myArray 4 now, this is the index of the array. So when we declare the array, this is how big the array is. When we talk about the array later, we're talking about the index of the array. So myArray 4, if we have a look on here, 0, 1, 2, 3, 4, actually has a value of 0. So we should see that it is legal and has a value of 0. Now it is pretty easy to get confused by thinking this is the 4th element in the array, 7 is the 4th element, but just remember when we talk about arrays, we talk about the index of the array. So indexes start at 0, so the 4th index has a value of 0. Now does anyone have any questions on that, what we've just been through? Or did you want to add anything to that, Matt?
No, I think that's pretty good.
Awesome, cool.
All right.
And do we have any?
Josh, I have some question.
Yeah, sure.
Yeah, if suppose my array size is 7, so that means in all it can have 7 values in it.
Yep.
If suppose I'm trying to find my array 8, there's nothing like array index after bounds. So in this case, what output am I supposed to get? Or it will be completely unexpected?
If you wanted to say, if you wanted to say myArray 8.
Yeah.
Yeah, so it doesn't exist. So you'll get an error there.
So there's two things that may happen. You may read a random piece of memory and just get a random number, or you'll segfault.
Yeah.
Okay.
Because yeah, we're trying to talk about these things here, but it's actually not in our array, so yeah, we're not allowed to do that.
So if the memory is your memory,
Mm-hmm.
it won't segfault. It'll just print something random that is part of your program's memory. However,
Okay.
if it's not your memory and you're not legally allowed to read there, so you're reading from some other program, it will segfault. So you have to be really, really careful that you keep it within those bounds.
Okay.
And the other thing is, it's not just 8, it's also 7, because there is no index 7 in it.
Yeah, right. Anything other than 6.
Well,
Yeah,
6,
0 to
5,
6.
4, 3.
Yeah.
Yeah. Yeah, thanks.
That also includes negative numbers. Negative
Yeah.
numbers won't work at all.
Okay. Thanks.
Or floating points or anything like that.
Yeah.
Okay.
Cool. Any other questions on that at all?
No.
All right.
Awesome.
What I might do now to change the pace is go through some of the next assignment, and then we'll go to next week's content after that.
Cool. Did you want the screen back?
I've already taken it back.
I can't tell. So.
I know.
There we go.
I'm in control.
Hello, Josh.
Hey.
One question.
Yeah,
Can we
yeah.
go back? Can we go back to that question? Bit and bit lock, that one.
Yeah, definitely.
Yeah, in which we locked the bit 0, 1, and 4 and 7. I'm not clear about that.
Sure thing. Sorry, I'll just load that up on the screen here.
You're not sharing screens at the moment.
Okay. Yeah, just a second. Cool. So, sorry, I'll just try and find the right question.
It's quiz 5. Yeah, quiz 5 question first.
W5B1.
Yeah.
This one here. So this one on the screen here?
Yeah.
All right, cool. So let's go through this again. Yep. So we've got Lisa has an 8-bit lock. She calls it a variable named lock. And to lock the lock, Lisa wants to set some bits. So when we see the word set, we should remember from Lab 3 what operation we're thinking of. So we saw in Lab 3 that to set a bit, we need to use this OR operator. So straight away from the start, we can eliminate two of our responses. So we've only got these three responses left. Now, having a look, we said that we have an 8-bit lock. So that means that we've got 8 of these guys to work with. 6, 7, 8. And what we're saying is that Lisa wants to set some bits. So Lisa wants to set bit 0. Now remember that bit 0 is the rightmost bit. So we want to make this into a 1. Bit 3, so remember this is bit 0, bit 1, bit 2, bit 3. So we want to make that into a 1. And bit 7, so 0, 1, 2, 3, 4, 5, 6, 7. Alright, so in the lab, we're only setting a single bit at a time, but this time we want to set 3 bits at once. So we can see that all these responses are in hexadecimal. So what we actually need to do is we need to convert this into hexadecimal, this 1000. The easiest way to do this is using the calculator. So it's on any Windows computer. Windows 10 it looks like this. Windows 7 and 8 it looks a bit different. But
Justin,
essentially you'll load it up. Yeah?
do you want to just quickly show how you do it manually?
Yeah, I can do that too.
Jaws is 8B. Is it 8B?
It should be.
Yeah, it is.
If it is 8B, I think.
8, 9.
8, 9. 8,
8,
4, 2,
9.
1. 8, 9. Yeah.
Yep. So the way that we can do this manually is what we can say is this, starting from the right side for our bits, we can say that this is worth 1, this is worth 2, 4, 8, 16. Oh, this is to decimal, sorry. We're going to hexadecimal. Ignore
Yeah.
that. Yeah, if we're going to hexadecimal, what we do is we need to bunch our bits up into groups of 4. So here's 4 bits. Here's 4 bits. Now, what we can do is we need to convert or work out what this is. So again, what I was saying before is this bit here is worth 1. This bit here is worth 2. This bit here is worth 4. This bit here is worth 8.
Yeah.
So there's only a 1 on the bit that's worth 8. So that means that this just corresponds to the number 8.
Okay.
And same thing over here. This corresponds to 8, and this corresponds to 1. So adding this together, it comes to a total of 9.
89.
Yeah, and that's how we get our answer in hexadecimal. So this is 89 in
Okay.
hexadecimal. Yeah, so
Okay.
yeah, when we're going to binary to hex, it's quite nice. We just need to do groups of 4.
Yeah.
And then we can
0,
convert.
1, 4, 7.
Now, one other thing
Okay.
is that don't forget that in hex you've got 16 digits. So if you get
Yeah.
10, you're actually getting the letter A.
Yeah.
Yeah,
After 9.
correct. Yeah,
Okay. Okay. Cool. I got it
Yeah.
now.
awesome.
Okay.
And then of course we know that setting, so it should be our answer here. Awesome. That answer your question there?
Yeah. Thank you. This
Yeah.
one.
Fantastic. No problem.
Okay.
All right. I'm going to. Is there any other questions regarding the quiz? No. All right.
Cool.
We'll go on to
Awesome.
the next stage. Let me grab it up. Big scary assignment. It has got draft written on it. There may be slight changes, but unlikely. All right. So it's the same as last time. There's the code, and there's the written portion. Now, with both of these, especially the written portion, make sure you read the feedback. Okay? A lot of you that are doing engineering are going to have to write a lot of reports. If you're doing VIT, you also need to write a lot of reports, especially when you get to the end. So make sure you get the feedback for this and take it seriously. If you lost a lot of marks in the first one, don't stress. It's only 5%. But this one's really important. Next thing, don't forget, it's an individual assignment, so you can't work collaborative. You should only work by yourself. All right. So this one has a bit of background information. Now, what we've said here is that we're dealing with some electronics. And we're not expecting you to know exactly what this means. What we are expecting you to understand is the equations. And there's a mistake. No. That's right. Okay. So basically, the background is an alternating current circuit is one that the output of the voltage source changes with time. When we add components to the circuit, the voltage and current will be different at different points in the circuit. So, for example, we have a circuit. Don't worry if this doesn't make too much sense, but you should understand this is a circuit. You've got a voltage source here, and the current will be different here, will be different here, will be different here. The voltage will be different here, here, and here. Okay? So we're saying that it'll be different in different points. We'll get to some examples shortly. So here we need to know Ohm's law. If you've done physics, you should be aware of this.
Now notice that instead of R here, we've got Z. So you can think of this as complex resistance. Okay? There's three types of components. We have resistors, capacitors, and inductors. And the user can select any one of these. Once again, as long as you understand that they have different calculations, that's the main thing. If you're doing IEL, then we expect better comments. All right. So the resistance here for a resistor, its impedance, its complex resistance, is the same as its resistance. For a capacitor, we need to calculate the reactance to get its complex impedance. So this is complex numbers, and this is something we'll do in the next lab. We'll show you how to calculate all this, and you'll create the functions so you don't have to work this out manually or anything like that. And inductors, very similar. There is a mistake. That should be an F. You've got a different equation, and you've got a different impedance value. You can see that they're very similar. However, capacitors, you've got 1 over 2 pi f c, where reactance for inductors is 2 pi 6 f l. And then you've got the impedance values for capacitors is minus j, and for inductors it's plus j. Now, if you've done complex numbers already, most people should have covered already, you will see when you've done complex numbers, you've probably used I. So for electronics, we use J instead. And the reason being is I usually stands for current, so it's not as confusing. Even though it kind of makes it more confusing. All right. Now the components, as we saw in the, I think it was the lab 1, we saw 2 resistors in series and 2 resistors in parallel. So this is the same here as well. So 2 components in series is like this, where 2 components in parallel are like this. Okay? And they both have different equations. So here, to calculate the total impedance of a series, we have Z1, Z2, and basically ZT total equals Z1 plus Z2. Now, if we have 3, we can do it in multiple equations. Or if we have 4 or 5 or 6, however many, we grab 2 and we calculate the total here, and we can represent that as being a single one now and just calculate the next one in series. So this would be Z3. So the new total, so total 2 would equal Z total plus Z3. Same with components in parallel. If we have multiple, we just calculate 2 and then calculate them 2 against the new one, and so on. So if we had these 3, we'd calculate these 2 and then treat that as 1 and then add it with the next one. Okay, so that's basically what this says. So this is our parallel circuit, and this is our series circuit. So you are to create a program that allows the user to view the voltage, current, and impedance for each component, and the total voltage and current in either a parallel circuit or a series circuit. So it's only going to be one in parallel with n components, so as many as the components as the user wants, or a series one.
when they're all in series. You won't have series and parallel together though. So this is the worked example. What we might do, we might cover the worked example next week after you've done complex numbers. But let's go down a little bit because there's already stuff you can start. So we have function prototypes and includes. So you all know how to include your libraries. So you've got standard IO and standard. This is a new one. So it's std.lib, and there should be a .h there. This is why it's a draft. Then you can add all these function prototypes quite easily. You've done that this week. These two you will be creating. The last two will be developed. Last four will be developed in the labs. You're welcome to change the naming, but you cannot change the types. So where this is bracket 6 or this has got a star, you cannot change that. Once again, you can do this part already. It's quite easy, listing your name in the assignment. You can do this part. The program asks the user which circuit they'd like to evaluate, the frequency. I'm just going to mute you. The source voltage and the number of components, and store the results. All of these values are positive. You can assume that they're valid. And then you ask for the number of components, and you should be able to show, so if they enter a 1, so a 1 here, then you should ask them how many components are in parallel. If they enter a 2, it should say how many components are in series. Now, all of this you can do already. Okay, so all of this you can do. This part here, we'll show you a way of doing it early next week. That will be covered in the next lab. So you can't do that yet. So you can't follow that on. Now, you can do this. You can print the results. You can start doing that. So this is your function print results. And you will be able to start this after you do the lab. And this one, the last part, you'll need the lab after that. So the week 7 lab. Okay, but you've got enough to start. So if you can start getting something down, then it'll stop the stress later. Okay? Any questions?
Hello.
Yeah.
Yeah, Matthew, what is this std.lib library?
Okay, so this is another library. This is for us to use dynamic memory, which will be covered.
Dynamic memory.
So this library has a lot of things in it, but we need the function. Yeah, that's not a pen. We need the function. Oh my god. Why is it doing that? No. We need the function malloc, which we'll cover in week 7.
Allocate memory, yeah.
Yes, this is memory allocate.
Yeah. Okay.
Okay, and so this is where this step 3 comes in.
Okay, step 3.
Yes, so step
For
3
this library. Okay.
is where you'll need to allocate memory. Now, I will show you a way if you want to start early to do it without that, and then you can add it later. So what you can do is create an array which you know the size, and don't ask the user until you learn that thing if you really want to go far ahead. But you have enough to start. So I'd get a start on it. The marking guide has changed a little bit. Some of it's similar, but all this stuff is new. Because now we've got functions, pointers, pointer arithmetic, malloc, and then the outputs.
Now this one is worth a lot, which is your calculations. The marking for the report hasn't changed though. Okay.
Okay.
Any other questions about the assignment?
Not about this assignment, but about the last one, about the first.
Okay.
Can we talk about the bonus question now?
Yeah, of course.
Yeah.
Let me get the assignment up.
Okay.
Okay. Where are we? So that was week 4. Yep. All right. So
Matthew,
this is,
I mean, if I will do a bonus question, then I will get 110 out of 100.
so it's capped at 100, as in with the So with any assignments, whenever you go over, it will get maxed at 100. So if you get 160, it's 100. If you get 105, it's 100.
Okay. Okay.
Yeah.
Yeah.
So you can't go over.
Yeah.
All right. So the bonus was to handle the case that the user enters something other than 3 appropriately, and I did add in the further information that it had to be based on stuff you'd already done. All right. So I'm just going to move that. I'll move that. I'll move that. So we had some test cases. I didn't mean to do that. Which were in week 5 as well. Week 4. We'll grab the test cases up as well. Bonus question information. So these are actually the cases that we will test it against. So we had RE, F, 3.3, 2.2, 1.1, 6F, GF, Hello World with a space in the middle, 4.566, blah, 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 and then we hit the 1, which is correct.
Yeah.
So there is quite a number of ways to solve this problem, and when you learn some more things, it's actually an easy problem to solve, but given what you know so far, it's a little bit more difficult, but not impossible. So, when you were getting the numbers in originally, you would have been doing something like scanf, %d, input. Now, the problem with this is that this case would end up in an infinite loop. So with this case, in this case it would take the 3, it would take the 2, it would take the 1, it would take the 6. In this case it wouldn't work. In this one it would take the 4, and this one would work. Yep. Now, it would actually, given this, would repeat twice because it grabbed the next one. So if we have a look at this one, so we've got 3.3 in the buffer. So let's say this is in a while loop, and we'll say while inputs, well, not equal to a 1, just for the example. Okay, and we'll just set input equal to 0 at the start. Okay, so this here would grab this 3 first and would remove everything on the buffer beforehand. Then we go back up. Input is still not equal to 3. Forgot that. At 1, sorry. So it'll keep going, and it'll actually grab this 3 and will delete everything beforehand. So it grabs the 3, but it also deletes that dot. And then it'll be waiting, because there's a new line here, there's no other. So this is looking
and waiting for the next available int, which there isn't one at this stage. So we can't use that. Now, the case that we use so scanf is really bad at handling letters. It will actually leave the letters on the buffer and will keep looking at them same letters over and over and over again, and you'll end up in an infinite loop. Okay?
Okay.
Because it doesn't remove them, which is bad. So, that's not what. Let's look at what we can do. So the hint I gave is to treat everything as a character. The reason being is then we're just getting the raw data off the buffer or whatever the user types. And so we have no problems with conversions, we have no problems with anything, because a character is always going to be a character. So let's create two variables. Well, let's create a variable. So what happened? Right, so we create a variable called car. Let's call it. Let's call it the table type. Okay.
Okay.
Yep.
Yeah.
Then we will do a loop. Now, it's up to you how you want to do this. You could do it different ways. I'm going to do it this way. This is up to you. This is just how you want to handle it. If you wanted to do an if statement throughout the whole thing. So we'll say while not table type. And I'm going to have an if statement here to check the table type is correct. And if it isn't, it'll print out wrong. It won't actually print out wrong, it'll print out invalid input, but I'm not going to write all that. And it will set table type to 0, so that the while loop will continue around. So if it's wrong, then it'll keep doing this loop. Now I'm kind of running out of room. What we'll do, move this. Here. I think I'm using the wrong pen. Alright, so we've got a character. I don't know why there's that there. I hate when it does this. So we've got a character, table type. Now what we want to do is scan. So instead of %d, I'm going to use %c. So if I do this, I can now, in my if statement, say something like this. Oh. If it's not table type equals a letter 1, or table type. Now you could have done this differently as well. There's nothing wrong with this. 2, then it's invalid. Yep.
Okay.
Yeah. So if it's not the character 1 or 2 now, then it's
Okay,
wrong.
okay,
Yep.
okay. Okay, we are checking for only 1 and 2 here.
Yep. And then it changes it to 0, and it'll just keep going because 0, we know, becomes a 1. Okay. So this still won't help us because we're still only checking the first one. However, it does mean that these don't cause an infinite loop because it'll grab the R, it'll grab the E, and it will just say it's wrong. So what we need to do now is check the second character. So 1 and 2, it's not just 1 or 2, it's a 1 with a new line next to it. Because this one with a dot next to it's not right. So let's create another variable. So I'm going to call it temp. Just a temporary variable. So I'm going to scan the next line. Yep.
Okay.
Now what I could do here is add an and here and say and temp equals new line. Yep. Now that would work for this case, and it would reject this, this, and this, and this, and this. The problem, however, is it's going to accept this one and this one. Oh, these two, sorry. So we've got 2.2, sorry, on the buffer. The first character it grabs, we've got a new line, is the 2 and a dot. So if I had table type equals 2 and temp equals new line, which fails, so it's wrong. It will go back up and it'll grab the 2 and then the new line, and it will pass, but we don't want that to pass, do we? So what we need to do after we've done this is clear everything after. So how we can do that is get rid of all this, and I think I need some more room. Ah. So red scan F's there. I'm also going to make these smaller. Okay. Come on. Okay. So now what I want to do is check if temp is not a new line character, then I want to empty the buffer. So how I'm going to do that, given what we have right now, is not use something that big. I will say if temp is not equal to the new line character. Sorry. Yep. Then what I will do is set table type to 0. Now the reason I'm doing this is because I'm just treating it as a flag. You could do this using bits if you had a lot of flags to set. However, you don't have to do it this way. Now, what I want to do is continue getting all the characters until the buffer is empty. So I can do that in a loop. So do scanf %c and temp. Oops, that button's really annoying. And keep grabbing more and more characters until temp is actually equal
to new line. All right. Does that
Okay.
make sense?
Yeah.
So let's grab an example quickly. So let's say we've got 2.2. So table type will be 2. Temp will be dot. Temp is not equal to new line, so it'll do what's inside here. It will set table type to 0 now. So this, well, I'll do it over here. So this is table type, and this one's temp. So table type 0, temp is a dot. Yep. Now, we then scanf the input, and we grab the 2. So now we've got a 2 in there. 2 is not equal to new line, so it'll go back up here, and it'll grab the new line, which will be here. Now the buffer's empty. It will go down here. It's neither of these, so that's okay, and it'll go back up and ask us again and again and again until it's right. All right. How you handle the while loop and this case is up to you. The main thing is this.
Okay. Okay. Temp is
Some-
not equal to new line. Got it.
Because we need to loop through and get rid of everything. Now there is lots of better ways to do this, but you will learn them later when we do strings. And also there's functions we can use to do this as well. But at this stage we want to see if you could solve it using the tools you had. All right.
Okay.
Cool. Okay. So any other questions about the first assignment? No? All right. Is there anything you want to add to that, Josh? Oh, I closed
No,
all on this.
I read it. No, I think that's pretty good what you've said. So
Just give me a sec. I closed all on this.
sure.
Wait.
We need the elevator music.
All right. So, anything anyone wants to ask about this week's lab that we just did before I go on to the new topic? No, yes. I can't see YouTube. Is
Can
anyone
we
else?
talk about the next lab?
Yeah, we will. We'll go through the content for it. But I just want to make sure everything else is out of the way first.
There's no YouTube questions, so
Put that there again.
I have a question. I've put that up on YouTube.
There's no questions there.
yeah, it doesn't say there's any questions on YouTube.
Is it?
No, there's nothing there. I can't see anything. Josh?
No, I can't see anything.
Okay. Shall I repost it? Just a sec.
Okay. While you're waiting, just one other thing. If
Can you see it now?
have a look.
No, it doesn't. Not showing up on mine anyway.
Nope.
Okay. My question was, if suppose we have an array of size 2,
Yep.
okay, and it's a character array
It's character.
or any array basically.
Yep.
So, like last time in the quiz, we had array of integers.
Yep.
So if suppose I'm storing A and Z into that.
Yep. So you got int A2, and I go A0 equals the letter A. Yep.
Yeah. And A1 to Z.
Yep. Oh, whoops. A1 to Z. Okay.
Yeah.
Let's
If
have.
suppose I do, if
Yep.
suppose I do like A of 1 plus plus.
A of 1 plus plus.
Yes.
That's
What will
quite.
be the output?
Okay, so it depends what you print it as. If you print it as an int, it will be a number, but if you print it as a character, then we go to our ASCII table, and Z plus 1 is a right bracket.
Okay.
Z is
So in any
90.
of the case, it will take which will be the next one. Yeah.
If I take the next one, it'll be a slash, and so
Yeah.
on. And it'll just keep going until it reaches the end. Now, with an int, because, so, what am I doing? So with an int, it's got, so a 32-bit int has 4 bytes. Yeah?
Yeah. Yeah.
Character only has 8 bytes. So if you're storing characters, it's good practice not to use ints, because what you're doing is basically, this is Z,
Yeah.
all of these are 0. Let's just wait.
Yes. Oh.
Yeah?
Yeah, makes sense.
Yeah. And it's actually still the other way around, but it's Indian-less. Alright. Any other things?
There's just a comment on YouTube.
Hey, small question, why don't you use Microsoft Word to explain rather than Photoshop? Microsoft Word.
That'd probably be trickier, I would think.
Because we're drawing a lot of diagrams, that's why. And this isn't Photoshop as well. We can put the notepad next to it and do it that way, if you prefer. I can put a notepad there if you want, but I cannot show any directions or anything like that. So, don't know how helpful that will be. Alright, okay, so next thing we are going to do, oh, I lost LMS again. Yeah. Alright, let me get to where I was. Okay, what are we doing this week? Sorry. Okay. So, in this next one, we're going to look and start looking at pointers. So, what I'm going to do is create my program like I normally would. Hash include h in main. Okay. So I've got a normal function that we'd normally start with. And what we're going to do now is create a new variable. So I'm going to call it int a, and I'm going to set it to 5. I am then going to do something interesting. I'm going to write int star b, sorry. I'll call it b ptr equals the address of a. So let's break that up. Int a 5. We've got int star b ptr equals a. So how we're going to do this is we're going to draw what is called a box and pointer diagram. So before we've been just drawing a box and showing what's in it. But now because we're going to use pointers, we're going to give a little bit more information. So before I do that actually, when I create A, basically our program will look through memory and find a free space that has 32 bits. So say this is memory, and each one of these is a byte. And each one of these will actually have an address, which you'll get practice with next week. You will not know the addresses of where your memory is being stored. That's handled by the computer. But let's say this is address 0, address 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Now, when you actually run your program and get the addresses, they're not going to be as small as this. They're going to be a lot larger numbers. Now, let's say there's something in here already, and there's something in here already, and there's something in here already. So when I create this int a equals 5, it will look through memory and find the first 4 bytes to store A. So go through, and this is the first 4 bytes. So my A is now here. Now how the program knows where it is by this address. So the address is 4. The 5, 6, 7 are really irrelevant now because the whole thing is taking up this. So my address is at address 4. My variable is at address 4. So when I put a number in here, it will go into here. Now, I can find out the address by using this. So if I do printf, now you should write the addresses in hex, then it would print 4 out. However, if you run it really, it won't be that nice. It'll be a large number. Now, the actual address number, we won't know. Okay, it's just going to choose it. The computer's going to have its memory management unit chooses the value. You can force it, but you shouldn't have to, and it's not easy to do. So the problem is that we need to be able to store the address. And how we do that is by using what is called a pointer. So this here is a pointer. Now, the pointer is pointing to an int, okay? So the pointer itself is actually of size int because your memory addresses are ints. So each one of these addresses is actually 32-bit, but we want a pointer to an int. Okay, this gets a little confusing. So there'll be somewhere else in memory that we create b pointer equals the address of A. So it's going to look through memory. It's going to find, as I said, a pointer is always an int. I'll show you an example in the next part. So we'll look through memory and it finds the next 4. So it goes here. And what it will store is the address of A. So it's going to store that 4, that address. So basically what it is doing, it is pointing at A. The pointer itself has an address. So its address is 11. So another pointer could point at it. All right? Now, we don't want to draw diagrams like this because we don't
Sorry,
have to-
Matt, to interrupt, but can you please explain again from pointers?
What, everything?
No, not really. It's from the pointer is pointing to int.
Okay, so the pointer has the value 4, which is an address value. So you can think of that as being, it's pointing to this here. It's pointing to an int with the address 4.
Yes.
Yep. Now I'll
So,
show you.
whenever you are drawing that lines with yellow color, so that means you are storing A in that memory location, right?
So memory A is stored here. So if I put, if I put, let's say, the character A in here. Okay?
Yeah.
But
Yeah.
in the memory itself, it has an address. So that address is 4.
Yes.
And this here is pointing to that address. And it's pointing to an int. So the reason that we can't just go int b pointer equals the address of A is because we do this, we don't know what type A is.
Yes.
So let me do another example to show you. So what I'm going to do now is change this to a character. So what we've got is car A equals 5, car star B pointer equals the address of A. So here, let's draw our memory up again. And we've got address 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever. And let's say these 3 are taken up. Okay? So now we've got a character which is only 1 byte long. So it'll go here and take this one. So this is my A. Okay, and it'll store the value 5 in there. Yep. Then we create a pointer. Now, as I said before, the pointer itself is of size int. Okay, so it is this long. Okay, this car says that it points to a character. Okay, it's not saying the size of the pointer. A pointer is always an int. Okay, so the pointer itself, this is the B pointer, it will store this address, which is 1, as an int. But it's saying that it's pointing to
carry.
a character. Okay, a very big difference. A lot of students get confused and think that this should be this big, but it's not. Okay, a pointer is always an int until we get better memory one day. Okay, any questions so far?
Yeah, so this B pointer will be stored again, right? And that will point to or or the 4 bytes which you have drawn with the green line itself is a B pointer, and which is of type int, and it is pointing to memory location 1.
Okay, so be careful with your wording. This isn't of type int, it was size. It's of size int.
Okay.
Okay, it's of type car pointer. Okay,
Okay.
its type is this. Its size is the size of an
Int.
int. Yeah.
Oh.
Okay, because that is its type. But
Yeah.
whenever you have a star, its size is going to be as big as an int. Yep.
Yeah.
Okay. Now, these memory addresses, we're never going to know. Okay? Especially when we're designing our own code, stuff like that. So, to make it easier, what we do is draw a box and pointer diagram. So here, what we would do is draw the variable like this. So this is my variable A, that's its name. We then put the type here, and then we put the value in the bottom here. Okay, so this is a box diagram. When we create a pointer, because we don't actually know the address, what we do when we're describing and designing our code, we give it its name. So it's a B pointer. We say what type it's pointing to and what type it is. And because we don't know the address, all we do is we draw a circle and we point it here. Okay? Because we're never going to know the address because it's done by the computer itself. So if I create another pointer, caster C pointer, and also point it at the address of A, then I would draw another box, call it C pointer, caster, and then I would say that it points here. Okay? Because the value here could be anything. Every time you run your program, it may change. Well, it's likely to change. So it's not a set value. 5, it's always going to be 5 in this program. This, when you run the program another time, it may choose another place because that place was filled with the game you're playing or something. Now, what we can also do, actually I'll do that after. All right, so does that make sense, how to draw these diagrams? Does the diagrams make sense?
Yeah.
Yep. Cool. All right, what's next? Okay, so let me Okay, so now let's look at how this can be useful for a very simple case. So we're going to keep our 2 pointers here, and I'm just going to make them a little smaller. And I'll also make these a little smaller. Okay, so we've got our variables here and our pointers. Now what we can do is actually change what is in A by using the address. So when we've seen this symbol in the past, it's usually meant multiply. When we see it when we're initializing or declaring a variable, it means you're declaring a pointer. And when we use it before a pointer in an expression, it means that we're dereferencing it. So C is a little annoying. This has 3 uses, depending on where you use it. So if I say A times B, it's different to car star, and it is also different to A star star B. Okay?
Okay, Matthew, one question.
Yep.
Can't we take this B pointer as int? Just because you told us that it is a...
No. Okay.
Okay.
So no, we can't, because it won't. So we can write that, but it can't point to a character because this pointer needs to point to a character. Okay.
Okay, for character we have to...
So this is wrong because this is a character. So it can only point. This can only point to ints.
Okay. Okay. Int for int, char for char. Okay.
Yes.
And float for float. Got it.
Yep. There is also a special type that can point to anything, but that is for later. Alright, so dereferencing. Dereferencing means get the value that's at the place you're pointing at. So if I do something like, let me create another variable. So car C. And I do C equals 2 plus star B pointer. Okay? What I am saying here is this variable here, go to the place you're pointing at and get the value. And that's what this star means. Okay?
Okay.
So this would now be 5. And we've got 2 plus 5, so C would equal 7. Yep. This star operator is used for different things depending on where you use them. Okay?
Okay.
Now, if I want to store into A, so let's say I change C to equal 4, and I do star A equals C, what will happen is, oh, not star A, sorry, stuff that up. Star B pointer equals C. It will dereference this,
So it will go to where it's pointing, and it'll put the value C. So it's going to put the value 4 here. So we can change the value of A by using these pointers. Does that make sense?
Yes.
Cool. So let's look at another example. Oh, my shoulder. And then we'll go to multi. See if there's any questions on YouTube's.
Not at the moment.
Cool. Alright, where'd my... There we go. Alright. So, in this example, what I'm going to do is I'm going to create two variables, and they're going to be, one's going to be an int, and it's going to be int x. Actually, I'll do int a. I like a better. And I'm going to do car, and it's b. And then I'm going to create a pointer, int star a, and I'm, oh, not a. Let's call it a pointer. And it's going to equal the address of A, and I'm going to create a car pointer, and we'll call it B pointer, and it's going to equal the address of B. So let's draw our diagrams again. So we've got A, and it's an int, and I haven't put anything in it yet, so it's just a question mark. I've got B, it's a car, and don't know what's in there yet. Then I've got a pointer, and it's a pointer to an int. And then I've got B pointer, and that's a character pointer. Now, with your question before, I just wanted to add to that. So as I said, you should point to the same thing. You can actually point to the wrong thing, but you need to be really careful, and it can actually be useful. So if I have an int, let's say, and I have a character pointer pointing at the int, what do you think would happen? So this is a character pointer. It will actually just point to the first byte. So you won't get the full int.
Okay.
Yeah? And this is why you need to use the same types, because it's pointing to something. Now, if I used an int pointer to a character, so it's only this big, then it's going to grab other memory as well that we don't have access to. And this is why you will need to use pointers to the wrong things sometimes, but this is why we don't, because we're not actually accessing our variable. We're either accessing a small part of it, or we're accessing places we shouldn't. Yep. Q. All right. So let's say A equals 4, and then we say, I need more room. So we say A equals 4. Then we say, why is that happening? Then, what does that? Then we say star A pointer equals 6, and then I do star B pointer equals star A pointer plus 2. Does anyone want to have a guess what the value is inside B and what's inside A?
A pointer. Oh.
Right. Have we got an answer? Anyone?
No,
For B pointer or for B?
for B.
Okay, so for B pointer and A pointer, you will never be expected to know the value. Okay? Because as I said, it's a memory address, and the computer decides where it's going to store A and B, and A pointer and B pointer. So by hand, you're never going to know, and that's why we use this diagram that points at it, rather than an actual value. We wouldn't write, because we wouldn't write something like that, because it wouldn't make sense. Because every time you run the program, if you run it on a different computer, it's going to be in a different place in memory. You're never
Yeah.
going to get the exact same place. So you're not expected to know, and that's why we draw this arrow instead. However, we can know the value that's inside A and B. So let's have a look. So we start here, and now A has what in it? 4. Yep. We then go to this line, and we're saying, go to the, so we're dereferencing A pointer, which means go to the place that you're pointing to, and what I want stored in there is a 6. So A is now equal to 6. We then get here, and we're dereferencing B pointer, so go to the place that you're pointing at, and we want that to become A pointer dereferenced, so now it's 6 plus 2, so we've got 8 in here. Does that make sense?
Yeah.
Okay. If I didn't put this here, then I'm saying add the address with 2, and that could be any value. But because I've got that star there, it's saying go to the place you're pointing to and grab the value.
Sorry.
Okay. I know. C's kind of scary. Pointers is kind of scary.
That was my reaction when I first learnt C.
Yes, I remember. Okay. I think that's a pretty good example because it's got 2 types. All right. So yeah, be aware that you can point at things that aren't right, but you'll end up with problems. That's not... Okay. So now what we're going to look at is... Do you want me to go over another example, or do you want Josh to go over an example? Josh, do you want to go over a simple pointer example?
Okay, I guess I can do that.
No.
And also, can you please explain why should we use the same type for like
Okay.
char for char and inferent?
Okay, so I'll show you why very quickly. So if that's horrible. If I have my memory, something like that. Okay, so if I create, I hate how it does that. If I create int a, it will grab 4 bytes of memory. And I store in there a equals 4. So in memory, this would be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0. Yep. Now I create a pointer. So this is memory address 1, this is memory address 2, 3, 4. As I said, we won't know these. I'm just doing it as an example. So I create B pointer and I point it at the address of A.
Mm-hmm.
Now I've got my pointer, which is here.
Yeah.
And this is B pointer. And it is pointing at this address, 1. Okay? But
Yeah.
it's pointing at a character. So all it is pointing at is this, not this.
Okay.
Because it's expecting a character.
Yeah. Yeah.
So now, if I try and change the value, it's only going to change this value and not the actual value, because we've only taken a small amount of it.
Yeah.
Now, if I go the other way, and I have character B, and I have B, now C will probably stop you here. B equals 4, and I have int star A pointer equals the address of A, then I have a big int. Oh no, I have a character, sorry. I have a character, and this is my B, yeah?
Yeah.
Then I have my pointer, which is here. Now,
Yes.
I'm pointing at something that is this big, but my B is only here.
Yes.
And so it's going to grab stuff that it's not meant to. C will yell at you for this as well. The compiler will yell at you for doing this, or this.
Yeah.
Yep.
Yes. Thank you.
So it shouldn't let you do it, but you can get around it by using void pointers.
Yes.
I don't know what the error is. Actually, I'll just quickly check it for you. So if you
Oh.
try and do it,
Semicolon is missing.
no, shouldn't say that.
Space in stdyoh.
That is okay, I guess.
Okay.
The semicolon is missing after written.
Yeah.
A. Alright. Put it in examples. Two. Save. Okay, so it will give you incompatible pointer type, and it's only a warning, so it still is legal. Okay, so if I do cc examples, and I go cc minus 4, I do example 2, see, I get a warning, initialization from incompatible pointer type, caster, B pointer, and A. Okay?
Yeah.
Okay.
So it will still let you do it, but it will give you a warning and it may cause issues. And the reason I also say that, I think there's something wrong in Josh's quiz.
My quiz.
Question.
It's not my quiz. It's you.
Question W6, P4, and P5.
Okay, I'll check them out.
Yeah, P4, P5. For that reason. Okay, so now let's have a look at the next thing. Oh, do you want to do an example with multiplication? Because
Multiplication.
that's always funny. Multiplying
Okay.
2 pointers.
Yeah, I can do that. All right, I'll write something up.
You need to turn your screen on,
Yeah,
and I'll be back in 2 minutes.
cool.
Charge.
All right, so I'm just writing up a bit of code here. Just bear with me a minute. Right, this should do. Didn't say that. All right, so I've written up a small program here just to kind of go through what we've been through. So we've got an integer a has a value of 5. This is way too big. So we've got a equals 5. We've got a pointer to an integer, which is called a pointer, and that just simply points to the variable a. So go a pointer equals the address of a. And we could draw this up in one of the memory diagrams, but we won't worry about it for now. Then we've got the same thing sort of happening over here for... Cool, so we've got b equals 3. And then we've also got b pointer, which is equal to the address of b. Cool, so what we're doing on the next line here is we're saying we're dereferencing a pointer. So what that means is now we're talking about the variable a, and we're going to say it's equal to a multiplied by dereferencing b pointer. So this gets kind of confusing. We've got these two asterisks here. And that's the reason I put this in brackets, just so that we can really tell the difference. Yeah?
Can I please change the font?
Change the...
It is too small, yeah.
Yeah, it is too small.
Okay, is that better?
Yeah.
Yeah,
Yeah.
thanks.
Awesome. Thanks for that. So what we've got here on this next line here is, again, we're talking about, we're dereferencing a pointer, which means we're going to be talking about our variable a. And we're saying it's equal to a multiplied by, and we're dereferencing the b pointer as well. So we've got these two asterisks that are next to each other. And again, that's the reason why I put this in brackets, just so we can really tell the difference in what we're talking about here. So what we're effectively saying is we're going to look at what a is equal to. So over in our example here, a is equal to 5. So let me just write that in. So we've got 5 times, so we have this asterisk, we're talking about multiplication. And then we're dereferencing b pointer. So we look at b pointer, we see that b pointer points to our b variable, and we're dereferencing it, meaning that we're talking about our b variable here. So in place of this whole thing here, we're actually just saying 3. So this is something to be careful of. It can get a bit confusing because there can be a lot of these asterisks in a row and they mean different things in this one line of code.
Josh,
Yeah,
on line 8, I guess you forgot to mention pointer.
I did. Awesome. Thanks for that. I completely missed that. Awesome. So that is very important. Don't do what I just did. Cool. So what we've done here is, so we've worked out 5 times 3, which is 15. And what we're doing is we're storing 15 into the place that a pointer is pointing to. So what that means is we're storing 15 into the variable a. We know we're doing that because we're dereferencing a pointer. So what we're effectively saying on line 9 is a equals 15. That's essentially what line 9 is doing, based on what we've just been through. So once we get to line 10 now, when we're just printing out the variables, so we can see the variable a has changed because we've done an assignment with a pointer. So we'll be printing out 15 space, and then we'll be printing out the number 3, just because we haven't changed b at all. Does that make sense to everyone that's sort of following along?
Yeah.
Or does anyone have any? Awesome. Yeah. Does anyone have any questions on this pointer stuff?
Josh,
Yes.
another example.
Yes.
Scanf with pointers.
Cool. That's a good one actually. So, all right. Let me get rid of this. All right. So,
Oops.
user. Yeah, cool. And let's have please enter a number. Right, so this is what we're kind of used to seeing when we've been doing our program so far. So, we declare an integer, we say it's user input, we ask the user to enter a number, and we use scanf to look for an integer, and we store it in user input. Now, we've actually been using this sort of ampersand operator every time we've done that in the past. And what the ampersand means is it's actually the address of. That's what we call it. So what we're doing, when we actually scan in an integer, what we're doing is we're looking at where this integer is stored in memory by using the address of operator, and then we're storing the value of the integer we're reading into that place in memory. So what we can actually do is, if I make a pointer, let's just call it a pointer, and let's just say it's equal to the address of user input. What I've just done here is I've now got a pointer variable that is pointing to where user input is stored in memory. And notice how we do that with the address of operator, which kind of makes sense when we use it down here. So what I can actually say is, instead of scanning it into the address of user input, I can actually scan it into my a pointer, or into my pointer, which points to where my user input is stored in memory. Because what we're actually saying is this points to a memory address of where we want to store our user input variable. And effectively what we can sort of see we're doing is we're just replacing this with a pointer. So that was the reason that this whole time we've been using the ampersand when we're scanning in our variables. Same with characters, floats, doubles. We need to actually store it into the address in memory. But now that we've been talking about pointers and we know what pointers are, they point to a location in memory. We can actually use just the pointer. If we've got a pointer pointing to where that variable is stored in memory, we can actually just use the pointer to talk about where we want to store that variable. Does anyone have any questions about that?
No.
Yep. Awesome. So pointers are really, really handy. They're probably one of the trickiest concepts in C. So definitely make sure you do spend a while reading up on this pointer stuff, doing some practices, and asking heaps of questions, because this is the thing that gets so many students. And it's something that if you understand well, then you can do so much with them. But if you don't understand them, then it's very hard to sort of keep up.
Okay. Okay, Josh.
Cool.
Can you please tell how to print the address of user input?
Print out our user input.
Yeah, address.
The address.
Yeah.
Okay, so to print the address, you print out it in hexadecimal.
Yeah, in hexadecimal.
However, it isn't very useful information. You'll see it in the lab, but it's going to change often. So you could have done that, or you could do so if we where's my so I'll show you. I'll quickly get a program. Oops.
Cool.
Alright, I'm just going to quickly show that. Okay. Zero. So that's compiler. That's example 2. Okay, so come back everything. I hate how Windows does that.
All these other things.
Yeah. Where's the Hangout page?
Matthew and Josh, one question.
Yeah.
When I'm doing this with %x, it is giving error.
With what? It'll give you.
%x, yeah.
It'll give you a warning, but it shouldn't give you an error.
Okay. But when I'm doing p in the place of x, then it is not giving any warning also.
Doing what?
In the place of x, I'm putting p. Then it is okay. Is it okay? %p, address of a %p.
Yeah, you can use %p.
P also okay.
Yeah. So x is an unsigned int, so it's going to print
Yeah.
anyway. P is a pointer, so it just won't give you a warning. But either way, so for example, the output will just be someplace in memory.
Okay.
Everyone's will be different. So it's unlikely, unless you're doing something dodgy, you won't actually need to know the place in memory. All right, so now what I'm going to show you is how this can be really, really useful. So in previous labs, in the last lab, we looked at functions. So let's say I have a function, my function, and I have int A, B, and I create my function. And I return A plus B. Now, this here, this function, you can only return one thing. So what happens when I want to return more than one thing? This is where pointers come in really handy. So what I'm going to do is change this to a pointer and this to a pointer, this to void, and this to void. I'm not going to return anything. What I'm going to do instead is I'm going to change that as well. Change that to a pointer, and what I'm going to do is get my A and make it equal B. And I'm going to get my B and make it equal A. Okay, so up here I'm going to create two variables. So int x equals 9 and int y equals 6. and I'm going to call my function. I have to send a pointer, so I'm going to send the address of x, and I'm going to send the address of y. Then I'm going to printf send b, send d, x, and y. So let's now have a look what's going on. So in our program, we've got int x equals 9, int y equals 6. And this is inside main. So inside main, we can see where 9 and 6 are. Okay, so x is 9, y is 6, and let's say it has memory address 4, and it has memory address 0. Yep. Now, what I do when I call this function, so my function, is I send it the addresses of these two variables. So I'm sending the address 0 and 4. Okay?
Okay.
Yeah? Now the numbers do not matter. Okay? As I said before, the numbers do not matter. So just, you can think of that. So I'm sending the address of A and the address of X and the address of Y. Now when I get into my function, so now I'm in my function, these do not exist. My function can't see up here. Okay? But we have two new variables. So I can't do something like x equals 4 because x, there's no reference to x. Inside the function, there is no x. Between these braces, there is no x. Okay? X is up here in main. Okay?
Okay.
So what I have, however, what I have, however, is two new variables, which are both pointers, and one is A and one is B, and they're both pointers. Now, when I send these values to this function, I'm sending the addresses. These are both pointers, so they can store the addresses. And so what I am doing by dereferencing A and dereferencing B is it's saying, go to the memory where this is, even though I don't have the name, and change the value. So up here, I don't know that it's called X. It's just some piece of memory, and I'm changing the value of A to the value of whatever's inside B. So this would become a 6, and then I do B star equals A star. So I put whatever's inside whatever A is pointing to into whatever B is pointing to, which is 6. So when I return from my function and print, it's going to now print 6 and 6. So I don't actually need these variables to change the value of what's inside them. Now, this means that I can return more than one thing from a function now. Does that make sense?
Okay. Okay.
I wonder if there's another good example. Okay, so let's look at another example. Let's delete all this.
Um, um,
Actually, that's a good example.
okay, so my function, I'm going to change it. And I'm going to put just a normal int here. And I'm going to do this. So now I'm going to send the value of y instead of the pointer. Does that make sense? Yep. So now I've got int x equals 9 once again, and int y equals 6. So in my memory, I've got 9, and I've got 6 at addresses 0 and 4. Okay, and one's x and one's y. I then call my function. Now, the first argument is sending an address. It's sending the 0, or whatever address it is. The y is sending a number. So it's sending a 6. And actually, what I might do is change this to 8, let's say. So now we go down to our function. So I've got my function. And we pass our address to our a variable, and I pass my value to my b variable. So now I have two variables. One's a pointer, and it's got the 0 address in it, and my other one has the value 6 in it. Now remember, we can't see above this line, so we can't see these x and y. So if I try and write x, it's going to say it's undefined. Okay, so now if I do star a equals b, it's going to take the 6 from here and go to the place that a is pointing to. It's pointing to here, and it'll change it to a 6. b equals 8. It's going to change this to an 8, but it has no relationship with this y, because this and this are two separate places in memory. Okay, so when I return to the function this time, it's going to print, well, it's going to print 6 and 6 again, even though I said b here.
Yeah.
Yep. Cool. Now, the other thing to be really careful of is if I call this x and y, regardless, let's get rid of pointers right now. And I say x equals 9 and y equals 8. Oh, x is already equal to 9. That's a bad example. Okay. But this example, we're not even looking at pointers. But something really important. Okay, so in my main function, I didn't mean to do that. In my main function, I have int x equals 9. So I have x, and it's got a value 9 in it. And y, it's got a value 6 in it. Yep. Then I call my function. With a 9 and a 6. And then what I do in my function is I have int x and int y. And I pass the value 9 and I pass the value 6. So this is called passing by value. When you're passing the address, it's called pass by reference. So now I create two new variables, one called x and one called y. And I store the value 9 and I store the value 6. Then I set x to 12. So this becomes 12, and I set y equal to 8. Then my function ends, doesn't return anything. What is it going to print?
It is again gonna to print 9 and 6, I think.
Beautiful. Beautiful. Yes, it will print 9 and 6 because this function ends. There is no reference to these x and y's anymore. These haven't changed. These are in a completely different place in memory. Cool. So it's really important. All right. One more thing about pointers, and then what we might do is okay. So one other thing about pointers. Let's get rid of this. Okay, so I'm going to have my variable. I did it again. Int a, and it's going to equal 5. And then I'm going to create my pointer. So I'm going to call it pointer x. And that equals the address of A. Now, once again, if I should draw it smaller. I have in my box and pointer diagram, I have the variable A, has the value 5. Oh, whoops, that was silly. It's of type int, and it has the value 5. Then I have a pointer. So this is pointer x, and it's an int pointer. And it has the address of A, so we just draw blue. We draw a dot, and we point it at this one. Yep. Now, if I want to point to the address of this pointer, because the pointer itself has to be in memory, I can create a pointer that points at an int pointer by saying int star star. So now I've got pointer y, which is the address of pointer x. So now I've got another pointer. Let's do him here. And this one is pointer y, and it's of int star star, and it points at a pointer of type int star. So it's a pointer to a pointer. Now, if I want to get the value and dereference this, then what I'm going to have to use, if I use this, is 2 stars to dereference it. So if I wanted to go and change this value to a, let's say an 8, using pointer y, then I would have to do star star pointer y equals 8. And what that is doing, this first one dereferences it so it's here, and the second one dereferences it so it's here. So now the value here will change to an 8. Okay?
Okay.
So if I had another variable, let me delete some stuff. remove some stuff.
Matt, can you please explain how to dereference?
Okay, so dereference is there's my pen. So to dereference, it's just the star at the front of the variable. It has to be a pointer.
Yeah.
So if I want to, so this is pointer x. If I want to dereference it and get what it is pointing at, then I put a star in front. So star pointer x is basically saying this location. So I'm treating it like it's A. So if I say star pointer x equals 8, then this variable will change to 8. Because this one here is pointing to a pointer, to change this A, I need to go down 2 levels. So now this would be 9. Now, one other thing. Does that make sense, Bella?
Yeah.
And same if it was on the other side of the expression. So if I did, let's say int c equals star pointer y, then my new variable c would equal 9. Yep.
Yeah.
Cool. Now, what I'm going to quickly do is introduce a new variable called b. So now I've got int b equals 5. So I draw another box. Oh, 5. And this is actually still 5 as well. We should make them different values. Make that 6. Okay. And then I have another pointer. So pointer z equals the address of b. So this is pointer z, and it's of type int star. And it's pointing at b. Now if I do something like this, pointer y now equals the address of pointer z, then this is no longer pointing here, it is now pointing, oops, it is now pointing here. So now if I dereference this twice, it will change b instead. Okay? Now this pointer to a pointer is really handy when we get to arrays. I know you've done basic arrays, but when we get to more complex arrays and dynamic arrays. All right. That is I'm going to quickly check the lab, but that is pretty much all you need for the lab. Sure.
Sounds about right.
Blah, 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 blah. We're going to go through this in the lab anyway. Cool. Cool. Yeah, this is pretty much all the lab. Now, one other thing is just something. Give me 2 seconds. Is there any specific examples you want to show, Josh?
Not that I can think of. I think what we've covered is pretty much the main ones. It's really a matter of just doing them to really get it making sense.
Cool. Just trying to think. Okay, so this is just something to be just want to quickly go over scope. This has nothing to do with pointers. Well, it kind of does, but kind of doesn't. If I have int main, and I have my variable, sorry, backwards. Int x equals 4. And then I just put in some braces. And then I go int y equals 5. And then I do printf cent d x y. Will this code work?
No?
No. Because y is only available here. Now, one thing to be careful of is I want this. Int x equals 5. And then I print out, let's get rid of that. And this. What would get printed?
4.
And would this work? Is this legal?
No.
Josh,
Hey,
is this legal, Josh?
you're redeclaring x as an integer.
Is it legal?
I don't think so.
It is legal.
Really?
Okay. Yep. It is perfectly legal. Because these two have a different scope, you can actually redeclare the variable with the same name. However, everything inside these braces will use the inner declaration, where everything outside of these braces will use the outer declaration. So as soon as it leaves here, this x is gone. Now this is something really dangerous, but you can actually do it. So be careful and never redeclare your variables of the same name. Okay? Because this is really dangerous. This is a really dangerous code. Okay? But you can actually do it.
The more you know. It's interesting.
Yes.
Hmm.
It's the same with what's things like declaring functions inside of functions. It's dangerous, but you can actually do it. All right. Any other questions?
Matt, can we discuss a bit about storage classes?
What about them? What about them?
Sorry?
What about them?
General idea about it?
Um, are we doing that this week?
Not
Sorry,
this
11.
week.
Trying to see when we're doing
But it is covered during the lecture, so I believe there will be certain questions on that in the quiz, right?
Ah, yes. There will be one of them. There'll be the
Yeah,
post.
and Josh will make it more and more complicated.
Oh, Josh has made it so hard that he had to extend the time.
I did, yeah.
Yeah, you have to write the whole assignment within 15 minutes for his last quiz.
Yeah. Well, it's 25 now though, so that's okay.
Is it from next week?
So it's from this week.
Okay.
Now, Josh, do you want to quickly go over const?
Const?
Constant.
Sure, yeah. So, do you want me to share my screen or?
Yeah.
Okay.
Emails.
Can you see my screen?
Yes, I can see your screen.
Yay. Alright, so let's just get rid of this stuff. Alright, so we have another keyword that we can use when we're using variables called const. So what that's pretty much saying is we're sort of saying my int equals so what we're saying when we say a constant or a const is kind of what the word suggests. So we're saying that this variable here, we're not wanting to change it. We always want it in our program to be equal to the value of 5. So the reason that we do this, for example, if we wanted to maybe have a variable that represented the maximum size of an array, for example, we could say that we've got a constant integer that's equal to 5. And what we're saying is that because we're using this constant keyword, means we're never going to change our maximum variable to any other value besides 5. And what you'll find is when we use constants, we normally write the variable name in capital letters just to sort of, so we can tell the difference so that we're not going to change a variable. But essentially, yeah, the reason that we do this is just so we can have this at the top of our program. So maybe if we're running our program later on down the track, we want to change the maximum possible size of our array to 100, we can easily just change one variable, recompile our program, and away we go. So the main idea of using const is because we never want to change this variable inside our program. So we don't want to do anything like we never want to do that. If we're doing this and we're using a constant, we don't want to be using a constant. And it's not limited to integer either. This can be float, double, whatever we want it to be. So, for example, if in our program we might want to declare pi as a constant, so because we obviously never want to change the value of pi, we could declare it as a constant, and it would be so on. That's an example of where we'd use a constant, because we know that the value of pi never changes, so we make it a constant.
Sorry.
You good? Do you want to add anything else to that? That's
Okay.
Uh,
So there's a couple of things I want to add. I might actually take the screen.
just a sec. Josh, if suppose we declare a macro like has defined pi
Yep.
and 3.141 and something.
Yep.
Okay. Then by any chance, can we, does it work same like const?
Our define up at the top.
Yeah. I mean, can we change, so if suppose you write has defined, for example,
Yeah.
max 10, then can
Yeah.
we change the value of max in maybe some other function or maybe in the main? Is it possible?
The macro or for a constant?
The macro.
Macro.
Can we change can we change the value of max somewhere in the program?
I believe we can. You have to confirm with me in this map, but we can do that with macros. There's like we can redefine it or something.
There's redef.
Redef, that's it. Yeah. So there is something we can use to redefine our macros if we want to give them a different value later.
So let's say Josh enters. So on the next line, he writes hash ifdef, not in capitals.
Okay.
Let's say debug or something. Then capitals, Josh.
Sorry.
Then hash redefine. Max 4 or 20, and then end if.
So yeah, what we're saying there with this ifdef is if we've got a macro defined that we've called debug, then we're going to do this line of code.
So
Otherwise, we won't.
Often you'll see in a lot of people's code they'll have up the top an ifdef debug. So if that you're debugging your code, you'll have some stuff that will change. So if Josh goes up the top and writes define debug, then he's indicating that he's debugging the code, and he might change some of the values. So he can redefine it to 5. However, remember that it happens pre-compile time, so you can't change it while the program is running. It's only going to be redefined once. So it's either a 5 or a 3 when your program runs, because it happens when the program is compiled. So the reason that you may change it may be because you're doing something different. So you define the debug. You say, I'm debugging my code. And so if it's defined that way, or another one that's often used is if you're using a certain architecture, so then you'd go if architecture x32 is defined, then you'd redefine some other variable to something else.
Yeah.
Okay, let's steal something. Okay. Now, with Josh's const thing, be careful. This doesn't mean that you can't change it. You're just telling the compiler that you don't want it changed.
Yeah.
So if I have const int a, and then I do something sneaky like int pointer pointer a equals the address of a, and then I do start pointer a equals 4, I've actually changed the value of a const.
Yeah.
Okay? You can do that. The const in C is different, but in C, you can actually still change it. So you have to be very careful. It is just for your safety. Now, the other thing that I wanted to show is, so you should try and use it whenever you've got something that you don't want to change. And you should also declare your pointers. So if I am going to do that again, oh, what the hell happened there? Let's say I do that again. What I would do instead, so that I know it can't change, is I do, so I've got my constant int a equals 4. And what I would do is do a const int star pointer a equals the address of a, and that means that now I can't change the value of what's inside a. Now,
Yeah.
there is another type of const. If I don't want to, so I can still change the pointer here. So I can do something like pointer a equals the address of b. Okay? If I don't want to be able to change the address of this, then I would need to do int star const pointer a, and that's saying I don't want the pointer itself to change, but I still can change what's at the address. Okay? So if I want total safety, it would be const int star, well, wait, yeah, that's right, const int star const pointer a, and that is basically saying I don't want the pointer to change, and I don't want what's pointing to change. Okay?
Yeah.
So remember that you still can change what is being pointed to, even if it is a const. And if you want to, where you put this const when you've got pointers, changes what it does. So int star const means that you want what it points at to not change. And if you've got the const beforehand, I mean, if you've got int star const, you're saying that the pointer shouldn't change. And if you've got const int star const, then you're saying nothing should change. Okay?
Yeah.
I don't think there's anything that hard on the quiz, though.
No,
Then again, Josh is evil.
this is true.
All right, I think we're pretty good. Other than that, there won't be anything else. You won't need. We'll cover auto and all that kind of stuff later. You didn't put any others on, did you?
The quizzes, yeah.
Yeah, it's just const. Yeah.
Yeah, I'm not that mean.
Yeah. So the other storage classes, we don't do many of them, but we like to do. We won't do registers. We won't do auto. We might do static and extern. And we do header files.
Yeah.
Body cap. All right. So last things last. This isn't about C. This is about me being annoying. If you can, it would be really appreciated if you can put feedback in the early subject feedback. I know it says week 4, but yeah. It allows us to do things like this and other things, and tells us where we're at. It tells the school if we're doing a good job or a bad job. So, yellow. Roll. If you could do that, you'd be very appreciated. Yeah.
Cool.
So yeah, if you can leave the feedback here, it'd be really great.
Yeah.
Because we want, pardon?
Yeah.
Because we want to do stuff like this again next year, and for other subjects. But for anything in the subject, but yeah. All right. I think that's it, really. Anything else you want to add, Josh?
No, I think that's all I had for this one.
Sure.
Um,
All right.
yeah.
We'll finish the broadcast.
Okay.
Okay. You can stay in the chat if you want, but we're stopping the live stream. All right. I'm done.